Good evening everyone. We will continue the problem section from the last class. So here today we are going to solve the problem regarding XRT and crystal structure and Miller indices. Okay, so see the first problem. The orthorhombic crystal has magnitude of primitive vector A is equal to 0.2121 nanometer, B is equal to 0.184 nanometer and C is equal to 0.197 nanometer. If a plane with Miller indices 231 cuts an intercept of 0.2121 nanometer along x-axis, find the intercept along the y and z axis. Okay, so for solving this, here actually the ABC parameter which is given already. So C and the Miller index is also given, it is 231. So now we have to find the intercepts. So along x-axis, what is the intercept? It is already given, that is p value. Now we have to find QR, what will be along the y-axis, and similarly what will be along the z-axis. Okay, so for that, we know that the Miller index is 231. So we have to divide it 2 with everything, means all other coordinate. Then it will be 1, 3 by 2, 1 over 2. It will be 1, 1.5, 0.5. Okay, so now what you have to do? See, it is like along x-axis it is point is 0.121 divided by 121, so it will be 1, so that is corresponding to here. Okay, now similar way it will be what, 0.184 divided by q, it will be 1.5. So from here you can get the q value. Similarly 0.197 divided by r, that is equal to 0.5. From there you have to get the r value. So see here, totally p square intercepts will be 0.121, 0.123 and 0.394. So this will be the x-intercept, similarly y-intercept and z-intercept. So please go through the problem, then we will go to the next one. Now we will go to the second problem. X-loop wavelength 0.12 nanometer are found to undergo second order reflection at the vac angle 30 degree from LIF lithium fluoride crystal. Okay, so what is the interplanar spacing of the reflecting planes? So here if you see, the lambda value, which is the wavelength, which is given 0.12 nanometer, and the second order reflection, that is equal, so we can write n is equal to 2. Now see the Bragg angle, that will be 30 degree, and interplanar spacing d is equal to we have to find it. So for that, what is we know the Bragg's formula, it will be n lambda is equal to 2d sine theta. So from there we have to calculate d value, it will be lambda divided by sine theta. Okay, so here angle is 30 degrees, substitute that value sine 30 and 0.12, then it will get the answer 0.24 nanometer. Now we have the third problem. It is an X-ray beam wavelength lambda 1 which undergoes a first order Bragg reflection at a Bragg angle of 30 degree. and X-ray of wavelength lambda is equal to 97 nanometer undergoes third order reflection at a Bragg angle 60 degree. Consider that two beams are reflected from the same set of plane. Calculate lambda 1. Okay, so here what we have to do, the lambda value which is given, lambda 1, that is first order back reflection 30 degree and second order reflection is 60 degree. Okay, so we have to find the lambda 1 value. So we know that the lambda which is proportional, wavelength which is proportional to sine theta by n. Okay, so if you take the ratio between lambda 1 and lambda 2, what you will get, sine theta 1 times n2 divided by sine theta 2 times n1. So here sine value you know already, and n2 which order of the reflection we know already. So substitute those value, it will be 97 into sine 30 divided by sine 60 into n2 divided by n1. So substitute all the values and find the sine 30 and sine 60 and substitute, then you will get the lambda 1 wavelength value, it will be 168 nanometer. So that answer will be option C. Now we will do the fourth problem. A polychromatic X-ray beam having wavelength in the range of 100 to 140 picometer in is incident on a family of reflecting planes with an interplanar spacing 275 picometer at the Bragg's angle of 45 degree. At what wavelength will the planes give rise and maximum intensity in reflection? Okay. So see here, the wavelength range are 100 to 140 picometer. So the d value which is given 275 picometer and theta is 45 degree. So what will be the lambda value? That is the question. So for n is equal to 1, if you see n equal to 1, that n lambda is Bragg's law, we can use it. So n lambda will be 2d sin theta, that is equal to 388.91 picometer. Similarly, for n equal to 2, what will happen? Lambda is equal to 194 and n is equal to 3, lambda is equal to 2 by 3 d sin theta we have to give. Then that will be substitute all d value and theta value, then we can get the 129.63 picometer here. So please go through it. So now we will go to the fifth problem. X-ray incident to 111 plane of a single cubic crystal with lattice constant of 0.2 nanometer. The first order reflection is observed at the Bragg's angle 43.5 degree. Calculate the wavelength of X-rays. Okay. So here what we have to do, the lattice constant is given, Bragg angle is given, lambda value we have to do. So first, for getting the lambda value, we know that Bragg's formula, it will be n lambda is equal to 2d sine theta. We need the d value. Okay. So for finding d value, that will be about a divided by root of h square plus k square plus l square. That will be a is 0.2 divided by HKL is 111. So we can write, it will get it 3 root 3. So root 2 0.2 divided by root 3, that will be 0.115 nanometer. Okay, now what you have to do, for n equal to 1, you have to substitute lambda is equal to 2d sine theta. You can substitute 2 into d value and sine theta. So it will be C2 into 0.115 into sine 43.5. You have to use the calculator and find that value. And it will be approximately 0.159. So the answer will be option D. So see, till now, so we have solved the problems related to that 111 primitive crystal, and mainly due to the XRD. Okay, so here if you see, all the problems are like, one case we have to find the wavelength, other one is the interplanar distance and the Bragg's angle also. Okay, so you should know the formula, how the first order and second order and third order reflection which will connect with the wavelength. Now if you see the eighth problem, it's a simple cubic crystal illuminated with X-ray of wavelength 0.09 nanometer and the first order reflection occurred at Bragg's angle of 8.8 degree from the 100 plane of the crystal. Find out the Bragg angle for the first order reflection from 110 crystal plane of the same crystal. Okay. So if you see here, here what are the parameters which is given? The lambda wavelength which is already given. Okay, and value it is first order reflection, Bragg's reflection, so n will equal to 1, and Bragg angle that will be theta 1 is equal to 8.8 degree. Now HK which is given 100. Okay, and Bragg angle theta to 100 plane, that H2 K2 L2 we can write. Now we know that n lambda is equal to 2d sine theta. From there sine theta is proportional to 1 over d. Okay, now if we take the ratio of the sin theta 1 divided by sin theta 2, what we will get d2 divided by d1. And we know that the d formula already I have explained that in second class how it came. So d will be a divided by root of h squared plus k, a square plus l square. So which means that d is proportional to a as well as d is proportional to 1 over root of h squared plus l square plus k square. Okay. Now take the ratio, you will get sin theta 1 by sin theta 2, that will be root of h1 square plus k1 square plus l1 square divided by root of h2 square plus k2 square plus l2 square. Now substitute theta 1 and theta 1 value here and hkl values for h1 k1 l1 and h2 k2 l2 here. You will get sin 8.8 divided by sin theta 2 is equal to 1 over root 2. Now from there sin theta 2 you have to calculate, it will be root 2 sin 8.8. So theta 2 will be sin inverse of 0.2163. So it will be theta 2 is equal to 12.49 degree. So this will be the answer for this question.
Madam, sixth and seventh question.
Which one?
Sixth and seventh question, ma'am.
Yes, this one.
Yeah. Hey, once again, sixth question is show me, ma'am.
No, numbering is different, that's why.
Okay, okay. No, not ma'am. Seventh one not noted. Okay, ma'am. No problem.
Okay.
Thank.
So please go through it, then we will go to the next problem. So this question which is different from the earlier question actually. Here we are taking the finding the theta value which is given, like we have to compare the two different condition and find the theta value. Okay. Now see the ninth question. A simple cubic crystal with lattice parameter AC undergoes transition into a tetragonal structure with lattice parameters AT is equal to BT is equal to 2 root 2 AC. Okay, so below a certain temperature, the ratio of the interplanar spacing of 1101 plane for the cubic and rectangular structure is. So see here, for a simple cubic, the lattice parameter we can say AC, and rectangular system where lattice parameters are AT is equal to BT is equal to root 2 AC and CT is equal to AC. Okay, now we have to find the D values, that is interplanar distance for cubic system as well as the tetragonal system. So for a simple cubic which is given that HKL value that is equal to 101. Okay, so we know that D is equal to A by root of H square plus K square plus L square, that is equal to AC divided by root 2. Now AC we know that A that will be for cubic, so AC D cubic is equal to AC divided by root 2. For tetragonal similarly HKL will be 101. Substitute the values H square plus 1 over root of H square plus K square divided by AT square plus L square divided by CT square. So substitute all the values, it will be 1 over root of 1 divided by 2 AC square plus 1 divided by AC square. So substitute all the values here, you will get root 2 by 3 AC. So we got the relation root 2 by 3 AC for tetragonal system and AC divided by root 2 for the simple cubic. Now take the ratio between these two, then that it will be like AC divided by root 2 times root 3 divided by root 2 AC. So you will cancel the parameters and you will get root 3 divided by 2. So the ratio between the cubic and tetragonal structure will be root 3 by 2. So now we will go to the another problem. The silicon has diamond structure with unit cell edge A is equal to 0.542 nanometer. The interatomic separation is, so it's given here. See the unit cell. So it's a diamond structure for the silicon. Okay, so you can see that, and the parameters, so you can see the atomic positions here from this, if it is origin, how it will be. Okay, now if you see the diamond structure, unit cell edge length is 0.542 nanometer. So in the atomic distance d, you have to find it. So see the atoms to this length will be 2r, that will be the d. So coordinate of the atomic in diamond structure, what it will be, 0 0 0, 1 by 4th, 1 by 4th, and 1 by 4th between the two atoms. Okay, so it will be 2r is equal to the distance formula we have to use, root of 1 by 4 a square plus 1 by 4 a square plus 1 by 4 a square. Then you will get the 2r is equal to root 2 into 1 by 4 a. So the interplanar facing d is equal to root 3 into 1 by 4 into that a value. It will be 0.542. So substitute that and multiply everything together. You will get 0.234 nanometers. So that will be the answer for this. Okay. So here you have to know how to find the get the distance between how the relation between the interplanar distance and as well as the radius of the two atoms. Now we will go to the 11th problem. The short wavelength cutoff of the continuous X-ray spectrum from a nickel target is 0.825 nanometer. So which is given here. Okay, now the voltage required to be applied to an X-ray tube is what, how much it will be. So here you have to know the other formula, that is equal to EV is equal to HC by lambda. So this is the important another formula for this X-ray calculation, means X-ray spectrum for the compound. So lambda will be 0.25825 nanometer. The voltage what we have to calculate. So from the formula itself, you know that the H is Planck's constant, light wave velocity, wavelength, and charge of the electron V will be the voltage. So it will be hc by E lambda is equal to V. So substitute all the values. We know already H value, it will be 6.6 into 10 to the power minus 34 into C value will be 3 into 10 to the power 8 divided by 1.6 into 10 to the power minus 19 into 0.825 into 10 to the power minus 9. That will be the voltage value. Substitute all this and Another calculation, you will get 15.37 into 10 to the power 2 volt, that will be 1.5 kilovolt for the, this much is the voltage required to be to be applied to an X-ray tube. Okay. Hello? I don't know how to check it.
Ma'am, I think screen is not visible.
Um, I hope it is visible now.
Yeah, now okay, ma'am.
Yes, yes. So please go through the problem, then we will go to the next one. Now we will go to the other problem. X-ray were produced by using the cobalt as target. It was observed that the X-ray spectrum contained a strong K-alpha line of wavelength 0.1785 nanometer and a weak K-alpha line of wavelength 0.1930 nanometer. Then the weak K-alpha line is due to an impurity whose atomic number is given. Okay, atom number you have to calculate. So we know that from the mostly slow, we know that 1 over alpha, 1 over lambda k alpha proportional to z by 1 whole square. Okay, so it will be what we can get compared to wavelengths. So it will be lambda of k alpha 1 divided by lambda of k alpha 2, that is proportional to z2 minus 1 divided by z1 minus 1 whole square. Okay, now here we know that the lambda values, the k alpha 1 wavelength, it will be 0.1785 nanometer. In k alpha 2 wavelength, it will be 0.1930 nanometer. So it will be what, if you take the ratio, you will get it Z2 minus 1 whole square divided by 27 minus 1 whole square. Substitute all the values and rearrange it. And if you see that, you will get the final answer Z2 is Z2 minus 1 proportional 25. From there, you will get Z2 is equal to 26. Okay.
Ma'am, please show me the solution, ma'am.
Yes.
Only question. Okay, ma'am. Thank you.
Now we will go to the Another problem, the target of an X-ray tube is subject to an excitation voltage V. The wavelength of the emitted X-ray is proportional to that. So here what is, we know that HC by lambda is equal to EV, that we have already shown the earlier problem. So from there we have to find the lambda value. Okay, so how to find it? Lambda is equal to HC by electron volts, which means lambda is proportional to the 1 over electron volt. So that is a simple problem. You have to know the formula, then you can directly answer for this question. Now we'll go to the next problem. An X-ray tube operates on 30 kilovolt, minimum wavelength of X-rays emitted. So here we have it been same formula only, have to H nu is equal to HCB. H nu is the energy, EV also energy. So we can write H nu max is equal to HC divided by lambda minimum, that is equal to in electron volt. Okay, EV means electronic charge into voltage. So lambda minimum will be what? HC divided by EV. That substitute all the values like 6H value, C value, and electronic charge and voltage. Voltage is given in the problem. Now substitute all that and do the problem. You will get lambda minimum, which is equal to 0.4125 into 10 to the power minus 10 meter. So lambda weight is 0.41 into 4.41 angstrom. Now let's go to the other problem. The K beta line of X-ray emitted from an atom with principal quantum numbers n is equal to 1, 2, 3, etc. arises from the transition. So it's like pure theory. So if you can read it, the characteristic of X-ray, actually what it is. Please read it, and here it's clearly written that the transition for K alpha line and K beta line, what it is. So that's the direct question. You have to understand, you will listen the SARS class and you will understand the basic questions. Okay. It will be some theory questions. So it's pure theory question. Now we'll go to the another problem. It's also little, every problem has, you should know only two or three formulas, but how we are applying the formula into the problem, that is the important part. Okay, so see here an X-ray diffraction experiment using copper K alpha radiation of wavelength 1.54 angstrom. The first reflection from an FCC is observed when 2 theta is 84 degree. Determine the indices from the reflection and the corresponding interplanar spacing. Show that the only one more reflection is possible. Determine the indices of the reflection and the corresponding interplanar spacing. Okay. So see here how to solve it. So lambda value which is given and 2 theta, the first reflection from the FCC 2 theta angle 84 degrees. So it will theta will be 42 degrees. Okay. For FCC, the ratio of h squares plus k square plus l square values which are 3, 4, 8. That's you should know about it. Okay. For odd number or odd even number it will be. Okay. Now, if the first reflection, what will happen? H square, first reflection, yeah, 1, plane. So it will be h square plus k square plus l square will be 3. Now the interplanar distance d is equal to lambda divided by 2 sine theta. So what will happen? Substitute the values, you will get the interplanar distance 1.15 angstrom. Now, so second reflection is on the plane 200. So it then do you have to, what do you have to do? You have to do the d111 value similarly and substitute in the A formula. So it will get A is equal to d111 root of h square plus k square plus l square. You will get 1.99 angstrom. Similarly, now if you now here from the first one, whatever the values given from the question, we calculate the A value. Using that A value, we have to calculate d200. Similarly, d220. Okay, so those two interplanar distance we have to calculate in each plane. So D should be the near to the lambda for the diffraction. So that's one criteria here. Okay, so this is the solution for that. So here, so please go through it. It is very important question. Okay. we go to the next problem. The powder camera of a radius 57.3 millimeter is used to obtain diffraction pattern of gold having a lattice parameter which is given. The monochromatic MOK alpha radiation of wavelength 0.71 angstrom is used. Determine the first four S values. So see here the values which is given. Those are R value which is given here in the question, radius, and lambda and A value. So the H square plus K square plus L square values for the first four reflection which is 3, 4, 8 and 11 for FCC crystal. So this you should remember. Okay. For the Bragg's law, for first order reflection 2D sin theta is equal to n lambda, and also we for the cubic system it will be DHKL is equal to A divided by root of H square plus K square plus L square value. Okay. Now if you see sin square theta will be lambda square divided by 4a square into h square plus k square plus l square. For h square plus k square plus l square is equal to 3. What will happen? It gives sin square theta 1 and substitute all the values here. Then you will get 0.0227. Okay, so theta 1 you got it. Similarly, theta 2, theta 3, theta 4 you have to calculate it. Okay, so it will be according to h square plus k square plus l square will be 4, 8 and 11. So you have to substitute that and get that. So then you will get the S value. So since radius of the camera is 57 millimeter, so S in millimeter that will be 40 degrees. So S1 will be 4 theta 1, it will be 34 degrees. Similarly, S2 will be 4 into theta 2, that will be, you will get it. Similarly, theta 3 and theta 4. So substitute all the value first. Okay, so this is the basic formula. From there you calculate theta 1 and theta 2, theta 3, theta 4, you are getting the same answer. If you get the theta values, then the calculating the S values are very simple. Okay.
Hello, ma'am.
Ah, yes.
What S values?
Hello? Hello?
Ma'am, tell me, ma'am.
What they asked? Actually, the net got stuck actually. Hello?
Okay, okay, ma'am.
I think S value only asked, I think. S value means like angle of scanning. Okay. Now I will go to the other problem. The primitive translation.
Tell
The primitive translation vector of two-dimensional lattice are A is equal to 2i plus j, B is equal to j. Determine the primitive translation vector. So it's very basic problem, whatever you have studied earlier. Okay, like I hope you reciprocal lattice formula you know already, that is A star is equal to 2 pi B cross C divided by A dot B cross C. Similarly, B star will be 2 pi into C cross A divided by A dot B cross C. So here A and B values are given. So A dot B cross C. So now we have to know the C value. So we have to assume the third transition vector C is the given the lattice along the Z axis. So we are taking C values as K. Okay, because A and B are in the XY plane. So C will be in the Z plane. And now substitute all the dot product and all do it. You will get A dot B cross C will be 4. And substitute that will be 2 pi divided by 4 into 2j cross K. Then you will get the answer. Similarly, B cross also you have to find it. That's it. It's just like in taking cross product and dot product, but you have to know, remember the formula. It's very important. I hope you know it's already in earlier like basic classes. So go through this problem. These are all very basic problems which I have given already. The direct vector and is given.
Wait for a few minutes, ma'am.
Yes, yes. Now we will go to the next problem. For a Na plus and Cl minus ion pair, attractive repulsive energies are E, A and E are respectively. Depends on the distance between the ions, that is R, according to EA is equal to minus 1.436 divided by R and ER is equal to 7.32 into 10 to the power minus 6 R power 8. Okay, for this expression, the energies are expressed in the electron volt per Na plus and Cl minus pair, and the R is the distance in nanometer. So net energy En is just the sum of the two above expression. Mathematically determine the equilibrium interionic spacing R0 and the bounding energy E0. Okay, so what are the parameters which is given? EA value which is given and ER given. So total net energy will be EA plus ER. So we have to add all those two things. Okay, so for finding that, we have to find the R0 value, which is R0 in the equilibrium condition. What will be the distance between the two ion pair? Okay. So for equilibrium condition, what will happen? dEn divided by dr is equal to 0. So take the derivative first and equate with 0 and find the R value, R0 value corresponding for it. Okay. So it will get it 0.236 nanometer. And now for bonding energy, what it will be? You have to substitute this R value. Means bonding energy means what? When R is equal to R0 at the equilibrium condition, what will be the total energy? That will be the bonding energy. So then substitute R is equal to R0 in the above formula. Whatever the total energy we have, net energy we have calculated, then you will get the answer. Energy will be minus 5.32 electron volt. Please go through this problem and note down it. following will be the projection of a vector onto the xyz axis are respectively a by 2, b and c, where a, b, c are the unit cell parameter. Determine the crystallographic direction within the unit cell using the following procedure. So first step is a vector of convenient length is to be positioned at that it passes through the origin of the coordinate system. Any vector may be translated throughout the crystal lattice without alternation if the parallel is maintained. So see here you can see a vector. This is the vector which we have shown in the first section, and measure the length of the vector projection on each three axes in terms of the unit cell direction dimension A, B, C. Say UA is the length on the x-axis corresponding, and UB means BB is the y-axis, and WC is on the z-axis. Okay, so all the projections you have to know from for the corresponding vector. Now, these three number U, V, W is the multiplied or divided by a common factor, reduce them is smallest integer value. So that's what we are normally doing in the Miller indices case. So this will be intercept will be half 1 1. Now we have to do what we have to do. We have to make it as a normal whole number. So now determine the crystallographic direction. These all three indices not separated by commas and are to be enclosed in the square bracket like UVW. So then you will get the answer like 1, 2, 2. So here the projected vectors are half 1, 1. So if you take the whole number from this, you will get 1, 2, 2. So that will be the crystallographic direction in the y-axis. Go to the other problem. Compute the interplanar spacing for the 1 set of planes in BCC alpha ion. The atomic radius of the alpha ion, which is given 0.1241 nanometer. Okay, so we know that the atomic for A to the radius relation for the BCC crystal, it will be 4r divided by root 3. So r is given, so you can calculate the A value, which will be 4 into 0.1241 divided by root 3. Okay, if you substitute the means calculate this value, so you will get 0.2866 nanometer. Okay, now the interplanar distance formula we already know, d11 will be A divided by root of h square plus k square plus l square. It will be 1 plus 1 plus 1, so it will be A over root 3. Substitute A value and you will get the final answer 0.1655 nanometer. So this will be the and interplanar distance for the 111 plane. are the problems we have gone through today. So normally, most all the problems are related to the X-ray diffraction. So if you see here, first problem, which is we have to calculate the intercept, find the intercept for the x and y axis, finding intercept. So that all problems like finding intercept and angle, order of the reflection, this you can get it from the Bragg's law of refraction. Now another one, which one problem which we have gone through today, it is lambda while calculating the wavelength. So for that you have to know the relation between wavelength and the angle of the incident theta value. Okay, and another problem which we have discussed today, that is the relation between the theta and d value. So here we know that theta is sine theta, which will be proportional to 1 over d, and d value you can calculate the independent distance d, that is you can calculate divided by the formula a divided by root of h square plus k square plus l square. Okay, now the another, and is everything is like most of them are formula will be same, but you have the approach how the questions given and how the comparing. Some problems are like this ninth problem, simple cubic values and tetragonal structure values which is given, you have to take the ratio of that or interplanar distance. So for that you have to calculate the interplanar formula for both the crystal structure separately and follow it. And this is another formula which we have done today, that is HCl by lambda is equal to EV. So here all the H and C and E are the constants. So the varying parameter will be the wavelength lambda and the voltage. Which is the voltage required to apply the X-ray tube. Okay, so most of the problem, the values which is given, you have to calculate using the formula. And another relation what we have gone through today mostly is slow, which will be the 1 over lambda that proportional to z minus 1 whole square, which is also related to the X-ray diffraction wavelength. Okay. So I am giving two more problems to solve, so you can solve it for the next class. So these are the two problems which we have similar kind of problem we have solved today. It's more than 2-3 problems similar kind. So you can note down these problems and these two problems and solve for the next class. So today we are winding up the class. We will see you the next week. So please try to solve these two problems for next class. We will discuss the answer in the next week.